When we read through that problem, you'll notice nowhere in there we were given the constant of cooling for the cake. So that's going to be my first order of business, is going to be to solve for K. So far, so good? So to solve for K, I'm going to take that initial information. So it says the cake was taken from a 350-degree oven. Well, that's telling me the initial temperature of the cake. And cools to 125 degrees after 25 minutes. So that's a future temperature. So that's my T of T. And my T would be that 25 in a room at a constant 65 degrees. So that's the temperature of the surroundings. That's my Tm. Oh boy, I forgot my E in there, huh? I'm surprised Blake wasn't on that earlier. He probably was getting ready to.
Oh, yeah. Definitely caught that.
Yeah, totally. All right. First step is going to be to solve for K, so I'll subtract 65 from both sides. And I'll simplify in the parentheses. 350 minus 65 is 285, I think. We'll divide both sides by 285. I know this reduces, but it's all going into the calculator at some point anyway, so I'm not too worried about the reducing of this fraction. Next step is to cancel out that exponent base of E. What do I use to cancel out an exponent base? I'll use a logarithm. In this case, that specifically use the natural log, so that matches the exponent base of E. And then we'll divide both sides by negative 25. I like to write it as multiplying by a reciprocal, though, so that there's no confusion later on if I'm dividing that 25 inside the logarithm or outside the logarithm. So I'll just write it as multiplying by a reciprocal. So that's, what do we got? 0.6 or 0.0658. Cool so far? Now that I know K, I can answer the proper part of the question, which is asking me how long it's going to take to get all the way down to 90 degrees. So that's going to be my T of T. Everything else stays the same. The room temperature and initial temperature stay the same. My K is now, though, negative 0.0658. And now we're solving for T because it's asking how long. So subtract 25 from both, or subtract 65 from both sides. That gives me 25. 350 minus 65 is still 285. Divide both sides by 285. Again, I recognize that fraction could reduce, but I'm not interested in doing it because it's all going in my calculator at some point later on anyways. Natural log both sides, just like we have done before. Really the same process that we had last time, right? Since the variable, once again, is just located in the numerator, or I'm sorry, in the exponent. And we'll divide both sides by that value for K. And again, when I write my division, I'm going to write it as multiplying by a reciprocal for that same reason. When I type this into my calculator, I'm going to be a little bit more precise, and I'm going to use all the decimal points for K just because it's available to me there. Give me a little bit more precise answer. I got about 37 minutes. Does that feel okay, Blake?
Yep.
Cool. Who's next? Ends. 126. Okie dokie. Whatever. All right, this one is an equation, not a story problem. Okay. So a couple observations straight away. The first is that my variable that I'm solving for is located in the exponent, but also in the denominator. My first order of business is going to be to get that thing out of the denominator. So I'll just do a little cross multiply to do that. Cool there. We'll divide both sides by that, 150. I'll do a little bit of reducing that's super obvious, but I recognize there's some more obvious reducing to do, but I'm just too lazy to do it. We'll subtract 1 from both sides next. Well, maybe let's go ahead and do that. That's probably worth doing. So if I do that, I get 5/3. Cool there. And then I'll divide both sides by 95. 3 times 19 would be 57. And I'm just, because I'm not trying to use my calculator, because it's just, I don't want to keep toggling back and forth. I'm just doing this stuff in my head. You're cool with me? Yeah? Okay. What next? Maddie? Oh, no, I mean to solve the problem.
Oh, no.
Natural log is next. Excellent, thank you. That was clearly it did sound very much like next question. So don't, I see where you're coming from. I think I say what's next all the time after I finish a problem, so. And then it's calculator time, right, Enzo? Okay. 1 divided by -0.6 times natural log 1/57. And the decimal I get is 6.74-ish. How's that feel? It's all right. All right. Maddie, where were you at?
102.
Okie dokie. Okay, what you want to do first here, Maddie?
First we want to divide 96 by 3.
Yeah. I get 32 there. God bless you. You're welcome.
What was the answer to the last question? Sorry.
674. Is that Was that a good face or a bad face?
Bad face. I did something wrong. Sorry.
Okay. If you want to talk later, we can take a look at what's going on. You think it's into your calculator or the algebra? It's the algebra. I was saying I meant like typed in your calculator wrong kind of thing. That's always the first place to check. All right, Maddie, what's next?
Would you try to get 32 to an hour?
Okay, you could do that. It was the calculator?
That was me.
Oh, it was you typing it into the calculator? Right. Is 32 a power of 4, though?
No.
Not an easily distinguishable one, right? So you could do two things. You could notice that both 4 and 32 are powers of 2. So you could think about it this way.
Yeah.
Or, what's up?
Okay, yeah, no, I get that. I get that.
Or the other, what I would have expected to maybe be the more obvious thing to do, would just be to use a log base 4. Oops. Either way would be fine, Maddie. Probably using the log there would have been the, I think, more obvious way of doing that, but doing what we did also would be appropriate. Or if you had noticed that 32 is 4 to the 2.5, you could have done that too, but that's maybe not so clear. Who's next? Alrighty then. Let's get the good time started here. Who are my bankers in the room? No, nobody? Well, you should all have said yes because they make a lot of money and you could do a lot worse, right? No, but it does prevent a lot of sadness. You know?
People who say that money can buy happiness don't have enough money to buy happiness.
No, I disagree with that, but I think it does prevent a lot of headaches.
It opens the horizons of a person.
Buy happiness, however, it can buy things.
No, we spent how much on Notre Dame for education? Yeah, I'm still so miserable here.
Oh, that's so sad. You're smiling right now?
It doesn't to hide the pain.
Oh, okay. I see.
It doesn't buy happiness, it causes me sadness.
Oh.
Yeah, so I disagree.
But that presumes you'd be happier in a different school. Maybe just school in general.
Just the idea of sitting in a classroom is not appealing to me.
I understand.
Yeah.
That's fair.
Oh, standing in the classroom.
Maddie's got a good point.
You never said anything about
I
that.
never did, yeah.
All right. So section 5.5 is about financial mathematics. When we talk about financial mathematics, a primary area of concern is going to be the concept of interest. When we talk about interest, there's really kind of two types of interest. When I say interest, does that mean like something that fascinates you?
Can't be.
No. In this context, no.
It's the one you get based on, it's like a percentage that you get back based on how much you have.
Right. So that's one way interest is used. The other way interest is used is as a fee on the money that you borrow from a bank, right? Right? So in general, the way banks make money is, well, let's rephrase. Let's start with a different point. So why do you think banks pay you interest for keeping your money?
So that you can keep your money there.
Because you trust their business. Because don't they also borrow that money to give out loans to people?
That's the reason, yes, is that they take your money that you are storing with them, and they're going to use it to give loans to people or businesses. And the way they're going to make money off of that is that the interest rate that you're going to earn by keeping your money at the bank is less than the interest rate they're going to charge the people on their loan. So they're going to make the difference off of that. Right? That's a sense, like in a very broad way, the way a bank makes money. Does that make sense? Okay. So when we talk about interest, there's really two types of interest. The first type is simple interest. For simple interest, the interest is only earned on your initial investment. Bless you. Okay. So when we say simple interest, again, that's interest earned only from your initial investment. So the simple interest formula is future value equals present value times 1 plus the interest rate times the number of years divided by 100. Or if you just want to calculate the amount of interest earned, you can do the present value times the interest rate times the number of years over 100. Or if you've already calculated the future value, the difference between future value and present value is just the amount of interest earned. So let's look at a numeric example here. Let's suppose you invest $2,000 at a 6% interest rate. How much money do you have in that account after 3 years? Sydney? Sure. All right, so we start with our simple interest formula. What are we being asked to solve for?
The amount after a certain amount of time.
Okay, so in terms of the formula, which one are we looking for? Future value, yeah. So if you're looking for the account value after 3 years, we're looking for the future value. Okay, so where does the 2,000 going to go in? That's present value, very good. And the 6%,
The R spot.
that is the R. And then the N is 3 years. And then it's just calculator time. Hi, Mr. Salick. How are you doing?
Good, how are you?
Good.
Annie's here today?
She has not been in class today.
You guys got a test or quiz today?
Not in this class. Okay. You're welcome. So I get 2,360. Everybody's okay with that? How much interest then did we earn? Emily? $360, right? Just the difference between the future value and the present value. Easy, right? No big deal. Now, almost nobody does simple interest because, well, it's kind of a ripoff. Instead, what we'd like is that if the interest, instead of being based on only the initial account, it's based on how much money's in that account when the interest is calculated. So this is called compound interest, is when we do that. Do it that way. So the symbols here in the compound interest formula are basically the same as the simple interest formula with the exception of this new quantity K, right? We're told K is the number of compounds per year. I'm guessing that most of us have a bank account, right? Probably a savings account, at least. If you ever looked at your bank statements, you have. You'll notice that your interest gets paid probably 4 times a year is usually how that works. So that in that case, for most standard savings accounts, I think that interest is compounded quarterly, 4 times per year. So that when we talk about the number of compounds, that's what we mean there. So you're looking to figure out the value for K in a story problem, you're looking for words, right? Compounded annually would be 1, semi-annually, twice, quarterly, 4, monthly,
12.
weekly,
52.
52, daily,
65.
sounds like you got it. Also, it may be also worth saying bi-weekly, 26,
Oh, fine.
every other week. Why would every other week be relevant? How many of you have a job? You get paid every other week, right? That's why that term tends to be a relevant term in the finance sectors. Most people get paid every other week. Okay, let's look at an example. Oops. So our example says if you invest $2,000 at 6% interest rate compounded annually, how much money do you have in the account after 3 years? How much did you gain in interest? So this sounds like almost identical to the previous question except for one word, or 2 words, I guess. What are the 2 words here that are going to be important to us?
Compounded annual.
Yeah. So because we hear the word compounded, we know we're going to be using the compound interest formula as opposed to the simple interest formula. Okay. Let's just tackle the first part of the question to start. So when we say how much, what are we solving for? Future value once again. Oops, maybe I should do that. Okay. So what are we filling in for present value? 2,000. And for R? 6. Great. For K? 1. And we know that because it says annual, compounded annually. And for N, we plug in 3. Cool beans. Now, I'm not going to bother with the times ones in my calculator. Is everybody cool with that? So there we get about $2,382.03. Was that better or worse than compound interest? Better, right? The compound interest is $23.60. This is $23.82. So like $22 better over 3 years. Is that like little deal, medium deal, big deal?
Over the 3 years,
It's a little deal, right? $20 is like, whoa, whoop-de-de-doo. You know, it's like, yeah, it was a trip to Chipotle or something. Like, that's nice, but let's see what happens if we say do the same thing over 30 years. So I'm just going to go back and enter for my simple interest formula, update that so it's going on for 30 years. And I'm going to update my compound interest formula, so that's going on for 30 years.
slight difference.
That's a much bigger deal, right? If you're talking about basically, $6,000 difference. So what's going on?
You're doing like a power equation compared to like a multiplication.
Yeah, so
Really different.
that is exactly the right idea, but the math vocab is kind of poor.
Because one's exponential, the other's linear.
Yes, there you go. So this is like your simple interest linear equation. And here is like your compound interest exponential equation. So the longer the time period, like the greater the difference between them would be. And that compound, the exponential one, like once it takes off, like get out of the way because you're really making some money now. When you start getting into that vertical-ish part of the curve, it's like now we're in it. That's why they say like making the hardest $1 million to make is your first $1 million. Because after that, you got enough money to like really start making some money. Anyways, let's take a look at the effect of K. So again, we had mentioned that annual means k equals 1. Semi-annual would be k equals 2. We said quarterly. I did not, that's quarterly. Quarterly, k equals 4. Spelling is hard, guys.
It really is.
Monthly, k equals 12, especially like spell check and stuff has really ruined my ability to spell.
Yeah.
Weekly, k equals 52. Yearly, k equals 365. So let's take that previous compound interest problem and just kind of see the effect that different values of k are having. So I'm going to go ahead and just retype this with oh, yeah. Surely daily. Thanks, dude. That's a good one. I just got too excited thinking about plugging the k's in. So when k is 1, we got that same 2382 that we saw earlier. Now we're going to change the k to 2. Big effect, medium effect, little effect. What do you think? Well, let's see. $6. Something. It's an effect. Let's change that 2 to a 4 now. Let's see quarterly. So we gained $6 difference going from 1 to 2. Going from 2 to 4, $3. Well, let's go 4 to 12. That's almost a 3 or times 3 change. There we, I don't know, $2. Okay, well, let's go all the way to 52. That's like, oh, that's more than 4 times. Oh boy. That's more than 4 times. That'll make a big difference. Less than $1. If we go out to, well, let's do 365, right? That's so big. Right? That's like 5 or 7 times. 20 cents. So what are we seeing here? As that value of k is increasing, it's having less and less of an effect, right? Now, bigger values of k are certainly better, right? You're still getting some improvement, but it's not like a tremendous contributor to like the value of that type of interest, right? What if we add one more to our list here? What if I say we're compounding continuously? What value would k be?
Infinity.
Yeah, it'd be infinite. What is that going to do? Well, let's take our compound interest formula and just see. Okay? So I'm going to start by doing some clever rearranging. Now, the why I would do these rearrangings, you'll see in a moment. But like initially, you're going to be like, okay, why you would think to do that, I don't know, but that's okay. It'll come together here in a minute, all right? So I'm going to rewrite the nk in the exponent in the following way. I'm going to write it as 100k over r times rn over 100. Now notice I multiply those two fractions together, I still get nk, right? I haven't really done anything other than like write it in a weird way. And you look at that and you're like, okay, like sure, that's still nk, but like why are you even doing that? It'll become clear in a moment. I'm going to now make a substitution. I'm going to substitute that 100k over r. I'm going to replace that with an x. So if x is 100k over r, what is r over 100k? If x is 100k over r, what is r over 100k? 1 over x, right? Because they're reciprocals. Everybody's cool? So I can do that. Everybody cool? Just made a little substitution. Anybody recognize anything here? Specifically the piece in yellow? No? That's disappointing. We go back and we look at probably this lecture. Nope, must have been this one. There we go. You guys see that? We talked about it before. I was hoping we remembered, but that's okay. That's why we do it in the notes, right? So I'm going to use that here. Where this is going to be our formula for continuously compounded interest. So that gives us 3 interest formulas, right? We have simple interest, we have compounded interest, and then we have this continually compounded interest formula for 3 distinct scenarios. Okay, let's do a couple of numeric examples here. That's smaller than it was being before. I'll just zoom in. All right. Jack invests $800 into a savings account with a 5% annual interest rate compounded continuously. How long will it take for Jack to have $500 in interest? What 2 words in here am I most interested in?
Compounded continuously.
Yeah. Why do I need that? Because it tells me which formula I need to use. Okay. All right. Where's the 800 going to go? What's that? PV, that's correct. And the 5% is? That's my R, right? And what are we asked to find in here? How long? So we're looking to solve for n. So what's my future value going to be then? That's the last piece I need to fill in. Yeah, 1,300 is correct. So it would be the present value plus the interest. So that would be 800 plus 500. Everybody cool? Okay, let's solve for n. First thing I do. Divide by 800. I reduced as I went. Everybody's cool with that, I hope. Next up, what should I do next? The natural log. Excellent. Any questions why the natural log? Okay. And then the last step would be, yeah, multiply by 100 over 5, which is just 20. Or 9.71 years. Still doing okay, everybody? Yeah, Blake. Not at all. All right. Let's look at another example here. Not necessarily related to continuously compounded interest. Here it says you find an account that has 6.5 annual interest rate compounded monthly. What would the equivalent interest rate, or what would be the equivalent interest rate for an account that is compounded annually? Okay. So hopefully everybody's clear that we are going to be using the compound interest formula. Just the standard one, right? Okay. So the 6.5 goes in for R. And what's going to go in for K? 12, because it says compounded monthly. Is everybody cool so far? So what I'm going to do is I'm going to rethink about this instead as let's do like that. Is everybody okay with why I did that, or why I'm able to do that? Exponent of an exponent means multiplication, so I can take the multiplication and change it into an exponent of an exponent. And I'm going to take this piece now and just type that into my calculator. So I get 6.0067, we'll call it. Everybody's okay there? Now, if this is compounded annually, I would have that, right? Well, I guess, yeah. Everybody agree? So this piece has to equal that piece because everything else is identical. So I'll subtract 1 and then multiply by 100. And I get 6.7%. Would be the equivalent annual interest rate. Everybody cool? Regina? Yeah, of course. Okay. Questions so far? Still doing okay? So this is going to lead into some financial vocab time. Who's ready for that fun stuff? The first one is annual percentage yield. This is the APY. And this is basically what we've just done above. So it's the conversion of one interest to an annual interest rate. So if we take our process before and we kind of standardize it or formulaize it, it turns into this formula. So again, the APY is just your annual or compounded annually equivalent interest rate. And APY is really helpful because it's a good way to compare two possible schemes. So for example, if we wanted to say which savings account is the better investment, one that pays 7.8% compounded quarterly or one that pays 7.65% compounded weekly, I'm just going to convert these into APYs. So that I can compare them. Everybody okay with what I've done there? So that comes out to be 8.03 for the first account. And I'll just edit the other one. So 52, 52, and then 765. I got 794 for the other one. So we're asking for the better investment. Which one is the better one? The first one, because it's a bigger percent. Everybody's cool? Okay. Second or next vocab piece is an annuity. And an annuity is an account where into which a sequence of payments is made. So what does that sound like? There's two kind of natural things that we do financially that sound like annuities. One would be like saving for retirement, right? Like every month you're going to probably put aside some money out of your paycheck for retirement. And the other would be in paying back a loan. Like you buy a car on a loan and every month you have a payment that you have to make, right? Those are the two kind of things that are natural annuity things that would probably be the first things you would think of, where you're making a regular payment or a regular investment. Now, in particular, what we're interested in is ordinary annuities. And that's just where the size of payment is the same every time. So like if you're saving for retirement, you save $100 every paycheck. Or if your car loan is, $250 a month, it's always $250. You guys cool with that? As opposed to like, oh, I saved $100 this month, but I saved $125 next month, and then I saved $98 the next month, like where it's just bouncing all over the place. Makes life incredibly more complicated if it's not the, ordinary. We'll only look at ordinary situations. Okay. So our formula for an ordinary annuity so I have future value equals R times 1 plus I to the n minus 1 over I. So the new symbols in here is R. That's your ordinary payment. I, which is R over 100K. And then cap N, which is NK. And I'm not going to define all these things over again that we've been using the whole time, right? Future value, R, K, N, or lowercase n, are all things we've defined before. I'm not going to write them down again. Everybody's cool with that? Okay. All right, so let's look at an example. At the end of each quarter, Sarah makes a $500 payment into an annuity account. If her investments earn 7.88% annual interest compounded quarterly, what will the value of Sarah's annuity be in 20 years? So I heard annuity when I read that, so I know right away I'm going to be using my annuity equation. And if we're asking for the value of the annuity in the future, what are we solving for? Yeah, future value. Okay. So what's going to go in place for R? That regular payment or ordinary payment. The 500. Excellent. And remember that I is equal to little r over 100, k. What is the little r in this case? 7.88, right? And what is the k in this case? 4. Okay. And the n, well, we know the k is 4 already, and what's the lowercase n? 20 years. Everybody's cool? Now, I'm just going to write it down like this because it gets pretty jumbled when you try to write all the numbers into it in the same spot. Although that is what I'm going to do on my calculator, but like on a sheet of paper, it can get pretty hairy. So I'll do 500 parenthesis fraction command, and then 1 plus, I'll do the fraction command again. I'll type in my 7.88 over 100 times 4. I'll close my parenthesis. And then I'll do 4 times 20 in the exponent. And I'll have minus 1. And in my denominator, I'll do the fraction command again. 7.88 over 100 times 4. And I'll close my parenthesis. So I get $95,483.39. But it's basically just a plug and a chug, right? Now, what if instead of like investing, we're talking about figuring out a loan payment, right? So say I want to borrow some amount of money at some interest rate, and I want to figure out what my loan payment will be. That's another way where we can kind of use the same idea. So here I'm going to say that PV is equal to R times 1 minus 1 plus I to the negative n over I, where the PV here is talking about the principal value. You could think of it as present value, as in like that's how much I borrowed, right? Because that's the value of your loan presently. You know, like 6 months later, that's going to be less because you've made some payments to it. Everybody cool? And this is really just a rearranging of that previous annuity formula. Okay, so I think I have 2 examples left, and we're going to be donezo's, which is pretty good news. All right. Maria buys a new car for $18,500. What are the monthly payments for a 4-year loan if she makes a $2,000 down payment and the annual interest is 2.9%? So again, I heard it asking for the payments, so I know I'm going to be using this formula that we just mentioned before. And again, I used I in here. I is still the same thing. I used cap N in here. Cap N is still the same thing as the previous formula. I guess I didn't write that down above, but hopefully you would have assumed the same thing. I'm going to just say it aloud now and not go back and write it in there. Okay. So, we're going to be solving for, we want to know what are the monthly payments, so we're going to be looking for R. So what are we going to put in for the PV? What'd you say, Regina? Okay, not quite.
Oh, wait. 16,000.
Yeah, 16,500. Why? Yeah, you have to subtract.
Oh, no, it's not. Oh my gosh. I'm all over the place.
But that's right on. Again, the idea here, if most of us are probably unfamiliar of the act of buying, a car or whatever, but I'm essentially just, I walk in, I give the person my down payment up front, and then I borrow the rest, but I don't have to borrow this. If I paid for already part of it, I'm not going to take more money than I really need to. Everybody's cool there? Okay. What's I going to be? $2.9 over 100. And what's the K in this case? It's not 1. Yeah, so we don't look at the interest rate there. We have to look at how often the payments are happening. That's maybe a little different than the previous one. And the loan was for 4 years. Okay, so I'm just going to divide both sides by this whole thing. And that should give me my R. Cool. Calculator time. So I'm going to do the fraction command. And in the numerator, I'm going to take in the 16,500. The denominator, I'm going to do the fraction command again. In the numerator, I'm going to do 1 minus 1 plus. And then for I, I'm going to do the fraction command again. Oops. And I'll do 2.9 over 100 times 12. And I'll close my parenthesis there. And then raise it to the negative 12 times 4. And in the denominator, I'm going to type in the I. To do that, I'm going to type the fraction command again. 2.9 divided by 100 times 12. Again, the fraction command is your friend, but that takes a little bit of practice to get that in there the right way. So the payment there is $364.49. Everybody feel okay there? Now the natural next question would be, how much did we actually end up paying for the car? So let's add up our total costs here. What are the total costs for the car? We usually use red when I'm answering stuff. What did you pay when you got to the dealership? $2,000. Okay, and then what did we pay after that? $364.49. How many times did we do that? Every month for 4 years.
48.
48 times, yep. So we ended up paying $19,495.41. Oh, 49541. Cool with that? And then if I want the interest, that would be the total cost minus the price, right? So that's the 19,49541 minus the 18,500. So that's $995.41. What do you guys think? This is the end. So at this point, you guys should be able to do 139 to 184. Let's put that in for